Okay, welcome. I'm going to start today by talking about yesterday's FRQ. I'll look at part A first. So actually, let's look at the problem first. A particle moves along the y-axis so that its velocity v. So this is really important. And this was, some of you lost track of this fact as the problem went on, because the College Board and these AP exams, these FRQs, are going to give you different parts of a function. So it might give you the derivative, might give you the second derivative, might give you the original function. It's really important to keep in mind which function we're dealing with. So in this case, this is the velocity, which means this is the derivative of the position function. You have to keep that in mind. So when it talks about on part A, find the acceleration, we already know that this is the first derivative, so the acceleration would be the second derivative. In order to note that, we would say it like this, because you need to be really clear. A lot of you have been, again, when I was grading your FRQs, a lot of you were reasoning your way through things versus letting the math show you what's going on. So here, if we find the acceleration, you have to be very clear. You need to say that the acceleration is the derivative of the velocity, so that everybody's clear that you know what you're doing and you're not just doing stuff. So be very clear about your intentions when you're writing things out for these problems. So the acceleration of the particle at time t equals 2. Most of you did pretty well here. You found the derivative. First of all, of course, the derivative of 1 is 0. And then the derivative of the arctangent of e to the power of t is u prime. So in this case, the derivative of e to the power of t is e to the power of t. I'm going to move my negative so it looks a little more clear. So that's u prime over 1 plus u squared. There is the acceleration function. Now, the acceleration when t equals 2 is this. It's negative e squared over 1 plus e to the 2 squared, or 4. Without a calculator, that's as far as you can go. This question did not ask you to justify or give any reason for your answer, so you're done. That is a horrible highlight color, so I won't highlight. Okay, for part B then. Part B said, is the speed of the particle increasing or decreasing at time t equals 2? So I gave you that hint before that you need to check both the acceleration as well as the velocity, because the velocity and the acceleration need to be working in the same direction in order for this particle's speed to be increasing. We've got to be very clear about how we answer this question. So first things first, we can tell from above that the acceleration at 2 is greater than 0 from part A. Notice that I'm being very clear about how I know that. 1 plus e to the 4th is positive, so the denominator is positive. The numerator is negative. So I'm very clear. The acceleration at 2 is negative because we found that in part A. Okay, the next part now, the velocity. If we look at the velocity at 2, we need to do some reasoning here. We've got 1 minus the arctangent of e squared. And some of you got a little bit confused about this. Remember, for arctangent, we're looking at the part of tangent that is only between negative pi over 2 and positive pi over 2. Those are the restrictions for tangent. And tangent looks like this, because at pi over 2, we've got vertical asymptotes. So when we're looking at this, we're saying there is some angle where the tangent is going to equal e squared. And e squared is a pretty large number, and it's a positive pretty large number. So what we know is that tangent is going to equal e squared, which is 6 point something, in here somewhere, closer to pi over 2. And pi over 2 is approximately 1.57-ish. And a lot of you reasoned your way through it in different ways. But what I can say then is that this is 1 minus a number greater than 1. Some of you said it this way, which would mean that the velocity will also be negative at time t equals 2. Now comes the reasoning for your answer. The speed of the particle is increasing. Not it is increasing. Not the particle is increasing. The speed of the particle. I'm very clear about what it is I'm talking about. Is increasing, and also be clear about what we're talking about at t equals 2, since velocity and acceleration are negative. Okay, part C is what threw people for a loop, I think, the most. You had the right idea in A and B, just maybe you missed a little bit of something here and there. But part C is what really messed people up. Part C says, find the time where t is greater than or equal to 0, at which the particle reaches its highest point, and justify your answer. A lot of you said, oh, well, this is always increasing, so we know that it's always decreasing, it's always decreasing because the derivative was negative, so that's always going to be, that 0 is always going to be the highest point then. Well, in this part right here, that angle is less than 1. And when that angle is less than 1, 1 minus a smaller number than 1 gives us a positive velocity. So the particle, the velocity is not always negative. The particle is not always decreasing. So don't reason your way through, math your way through. So in the math here, we know that we should check the endpoint, t equals 0. And I think it told us at t equals 0, didn't it? Yes, at t equals 0, we know the y value is -1. And then the particle does increase for a while, because we know that the velocity is positive in this little region up until we hit an angle that has a measure of 1. So what we're going to look for, and very few of you did this, we're going to look for the critical number. And the critical number is where the derivative is equal to 0. So the critical number is where is 1 minus the arctangent of e to the t equals 0. That's the derivative. And some of you started to get here and then things got a little crazy. So if I try to solve for t here, I know then that arctangent of e to the t is equal to 1. I know that the tangent of 1 is equal to e to the power of t, and then t is equal to the natural log of the tangent of 1. That's a critical number. I think one person plugged this into the second derivative to use the second derivative test, because it's going to be really difficult to choose a point on the left and right of that value to use the first derivative test. So if we can plug this value into the second derivative is going to help us determine if the function's concave up or concave down at that point. So the second derivative was the acceleration. The acceleration was -e to the t. So -e to the t is the natural log of the tangent of 1 over 1 plus e to the 2t. So 2 times the natural log of the tangent of 1, like that. Okay, so if we do some reasoning here, we know some properties about logarithms and exponentials. E to the power of the natural log, since those are inverses of each other, we know that the numerator is negative tangent of 1. If I look at the denominator using a property of logarithm, so if I put this 2 back up on the log, And then that e and the natural log are inverses, so they'll end up canceling each other out as well. So we've got 1 plus the tangent of 1 squared. Okay, I know that the tangent of 1 is a positive value because we're in the first quadrant, but then that negative makes this negative in the numerator. The denominator, that's tangent 1 squared plus 1, that's positive. So that tells us that the function is concave down, which means that this point we found, our critical number, is a maximum. And because we know that the function was increasing for a while, up until the angle was 1, we know that this will be higher than its initial starting point. So this is how we say it. We say, since the particle is increasing from 0 to 1. Actually, we don't even have to say that. We use the second derivative test. Let's do it. Since we use the second derivative test, we might as well explain it. Since the second derivative is negative at t equals the natural log of the tangent of 1, we know the function is concave down. Since the derivative is 0 at this point, t equals the natural log of tangent of plus 1, or tangent of 1 is the maximum, what's the wording? Is the time when the particle reaches its maximum height. You didn't have to get that wordy, but we've got everything in there. The important things are the second derivative is negative. I'm going to use a different color here. So the important parts are that the second derivative is negative. That's important. We know that the first derivative is equal to 0. We know that we have a maximum height, and that maximum height is at this t value. If you just mention those things, that's plenty. Okay, that's enough for me talking. That's the FRQ. The next video will be L'Hopital's rule.